Welcome to a lesson on electromagnetism mathematics. All right, in this lesson, we're going to explore some of the basic equations of electromagnetism and applications of electromagnetism. All right, so the way it starts is with Faraday's discovery that a changing magnetic field produces current. But remember, the technicalities of it is a change in magnetic field produces an EMF, an electromotive force, and that electromotive force is the V inverter, and that voltage then produces the I. All right, so let's talk about this EMF. All right, our equation is this. This is the symbol for EMF. All right, the symbol, the units for EMF is voltage, and when C it equals delta, this thing. Now this thing is called magnetic flux. All right, and I think it's iota B, but I'm not really sure. I just always called it magnetic flux. That's what we're going to call it. So the amount of EMF we get, in other words, the amount of induced voltage, is equal to the change in magnetic flux per time. All right, so if the magnetic flux changes quickly, all right, then we get a higher voltage. If it takes a long time for it to change, then we get a lower voltage. And the way you can see that is, if you think back to our demo where we had the magnet going in and out of the coils, all right, if I go really fast, I would get a lot of current. The current would spike. If I went really, really slow, then the current would only go a little bit because of this equation. All right, if the current went really fast, this is that time is really small, so therefore this is high, and therefore that is high. If this is a big number, this is a low number, and therefore that's a low number, and that is going to be a low number as well. All right, so this is a pretty complicated equation. Let's look at magnetic flux first, because we can't solve any EMF problems until we figure out what magnetic flux is, what the equation of that is. So let's check out magnetic flux first. Now, before we get into the equation for magnetic flux, let's just talk about what it is conceptually. Magnetic flux is basically how much of the magnetic field is going through a coil of wire. All right, so it does depend on how it's oriented. You can imagine if the wire is like this, all right, what these two drawings trying to show. If the coil is like this, and this is the magnetic field, well, then you can see I have magnetic field going through there. But if I rotate it like this, then you can see that the magnetic field goes above and below it, but nothing actually goes through the coil. All right, so when the magnetic fields go through the coil, we have magnetic flux. If we have a coil and magnetic field, but the magnetic field lines do not go through the coil, all right, then we get zero magnetic flux. All right, and if we rotate these things, then we can change the magnetic flux, and that goes back to our lesson on the generator. As this thing rotates, it goes from having magnetic flux to not having magnetic flux, and that is what causes the EMF and therefore the current. All right, so now let's check out the equation for magnetic flux. All right, so conceptually the equation for magnetic flux is pretty simple. We got magnetic flux equals the magnetic field times the area of the coil. Now the shape of the coil can be different, so you have to calculate the area of that. What this equation does not show is the mathematics that involves the orientation of whether the lines can go through the coil or above or below. All right, I don't want to get into that math. We're going to keep this pretty simple because it's online learning. It's difficult, and we're dealing with math here. All right, so with that in mind, let's look at a simple magnetic flux problem. Okay, so in our problem, we can read that the magnetic field is 0.5 teslas, all right, 0.5 teslas, because it says it's placed in a 0.5 Tesla magnetic field, all right, and we can also see that the radius is 3 centimeters, which is 0.03 meters, and they want to know what is the magnetic flux, because it literally says what is a magnetic flux in a circular wire. So now we know that magnetic flux is equal to B times A. But what they did not give us was A. So we have to calculate the area of this wire. Now it says a circular wire. So that means we use the equation for the area of a circle, which is pi r squared. Once we plug those numbers in, we get pi times 0.03, and then we go, and that's squared. We go to our calculator, and we get 0.00283 meters squared. All right. Once we add that, then we can just finish out the equation, and it's just magnetic flux is equal to 0.5 times 0.00283, and that gives us a magnetic flux of 0.00141, and now we have to figure out the units. Well, that's pretty easy because we know the magnetic field is in Teslas, and area is always in meters squared, so this is Tesla meter squared. And that's how we calculate magnetic flux. All right, now that we know how to calculate magnetic flux, let's look at a problem to see how we can solve for the amount of voltage induced in a coil of wire. In other words, the amount of EMF that's induced, or that can be induced in a wire. All right, so let's look at an example problem. Okay, so in this problem, they're asking for the EMF in a square coil of wire with those particular statistics. So if we start with our EMF equation, EMF equals the change in magnetic flux over change in time. Well, what we don't know is the change in magnetic flux. All right, big deal. Let's go solve for it. Remember, delta magnetic flux always means delta, always means final minus initial. So delta magnetic flux means final magnetic flux minus initial magnetic flux. So what we have to go do first is calculate the each magnetic flux, final and initial, and then subtract them to get this. So let's go look at the magnetic flux. All right, so we will start with magnetic flux final. And what do we know about that? It says it goes to a final magnetic field of 2.5. That's the final magnetic field. So 2.5. And the area of a square coil would just be 4 centimeters squared, which is 0.04 squared. And this will give us a magnetic flux of 0.004, all right, Tesla meter squared. Now, on the other hand, we have our initial magnetic flux, all right, which is equal to, it starts out with a magnetic field of 0.5, and it still has the same area, 0.04 squared. And that gives us an initial magnetic flux of 0.008. So once we add that, we can go back to our initial equation for EMF and plug those things in, all right? So if we have this here, our change in magnetic flux, final minus initial, I'm just going to plug those numbers in here. That would be 0.04004 minus 0.0008. I know I wrote that wrong in the last one, but it actually is this when you go to your calculator. So we get a change in magnetic flux of, what is that? 0.004 minus 0.0008, 0.0032. All right, and then we can see this is going to be plugged in up there. And our time from reading the problem, if you can, I know it's hard to look back on a video, but it said it was 3 seconds. So then we can just plug that stuff in there and it becomes pretty easy at this point. EMF is equal to our change, which is 0.0032 divided by 3 seconds, and we get 0.00107. And remember what EMF is. That's the induced voltage that causes that current to arise. All right, so the units for EMF is volts. That's how you can remember what an EMF actually is. All right, it's like kind of like a fake voltage, but not really. It's a real thing. It's just not a voltage coming from a battery like most people are used to and think of. All right, so let's look at our next EMF problem. All right, now this is a pretty complicated problem. There's several parts to this, all right? They're asking for the current. Well, the only time we've seen a current equation is with Ver. They gave us the resistance, which is 10 ohms, and we need the current. Well, to get current, we have to get V. But they're not giving us a battery. They're not giving us a voltage source. They're giving us our electromagnetism, all right? So we got to calculate our EMF, which is the V in Ver. All right, so we go to our EMF equation, and we see we saw from our last problem that we have to calculate our change in magnetic flux first. So let's do the final and the initial magnetic flux. All right, which would be our final magnetic field is 0.25. All right, and the area of a circular coil wire is pi times radius squared, which is 0.13 in this case, squared. All right. And we can go to our calculator really quick. And this is annoying, 0.25 times pi times 0.13 squared. And we get, what does that say? 0.0132. 0.0132. All right. Now we do the same thing over here. Our initial magnetic flux was 1, all right, times the area did not change, 0.13 squared. And I'll go through this really fast. Let's see. Pi times 0.13 squared gives me 0.053. 0.053. So to get the change in magnetic flux, we might as well just do that right here. Or sorry, change in magnetic flux, sorry about that, equals our final, which is 0.0132 minus 0.053. And we can go to our calculator again, 0.0132 minus 0.053, and we get a change in magnetic flux of negative 0.0398 Tesla meters squared. And yes, there's a negative there, but big deal, all right? That's just going to tell us in general the direction of the current. And we really don't care what direction of the current. We already know that when we're dealing with electromagnetism, it's an alternating current, okay? So now let's plug that back into our EMF equation. All right, our EMF equation. And we have EMF is equal to our change in magnetic flux, which is negative 0.0398, and that happens over 0.2 seconds. So how much voltage is this thing creating? We have 0.0398 divided by 0.2, and we get about, it's 0.199, but let's just round it to 0.2. That's a nice easy number. 0.2 volts. Notice in this problem and last problem that we're not creating a lot of voltage. And one of the reasons for that is each of these problems has only been one coil. All right. And if you remember back to demonstrations with the flashlight and with the coil and the ammeter, there's a lot more than one coil. So what happens is this is the amount of voltage just in one coil. So if we want more voltage, we can just add more coils. And that's actually what we're going to do in the next problem. But that's why I just want to point out why the voltage is so low. All right. So if we move on with this problem, this is now our V inverter. All right. So we're looking for the current. This is our voltage. So now it's just 0.2 equals I times resistance of 10. And this resistor is only going to get so that divides over, like simple algebra, 0.02 amps. And there's our final answer. So that's a multi-step problem, and that's a pretty long problem. All right? Okay, so moving on with our equations here. This is our our basic equation for EMF. But if we start to apply this to our electric generators, the type that Tesla designed and made famous, all right, we have to work this a little bit more engineering. Now, it would take a while to go through all the mathematics, but what you can see a little bit of similarities here between this one and this one, all right? What we just previously mentioned was if you add more coils, the voltage will compound on each other. And that's taken in the equation here, all right, N. This is just the number of coils, all right? In the previous equations and the previous problems, we had an N of 1, so we kind of ignored it, all right? Now you can see here is the magnetic flux, BA. Now the time kind of combines with something else, because remember what's happening in this generator problem. That thing is spinning, it is rotating. All right, so how much it rotates per time is just how fast it's rotating, which is omega, all the way back from our rotational kinematics. When things are rotating, that was just its rotational speed. So it does matter how quickly you rotate the coils, or in that generator. All right, so with this fairly easy equation, let's look at a problem. All right, in this fairly easy problem, they give us everything we need for our equation. They tell us that it's 100 coils, it's a circular coil with a radius of 0.75 meters. It has a magnetic field of 2 Teslas, and it's spinning at a speed of 50 radians per second. So while we do EMF equals NBA, the one thing we do not have here is A. Well, we can solve that pretty easy. A is equal to, since it's a circle, pi r squared, 0.75 squared, and we go to our calculator really quick, and we get pi times 0.75 squared. We have 1.77 meters squared. So once we have that, it's a fairly easy plug and chug equation. EMF is equal to NBA equation is 2. A is 1.77, and omega is 50. And we can go to our calculator, all right, where we get an EMF. How many volts is this electric generator producing? 100 times 2 times 1.77 times 50 equals 17700 volts. That is a pretty strong electric generator, but it's pretty big. 0.75 meter radius is a pretty large coil, all right? And 50 radians per second is fairly fast, and this is a very large magnetic field, all right? But so it produces a very, very high voltage. And that's how we calculate how much voltage a generator makes. All right, now we're going to look at equations that govern transformers, a primary side and a secondary side. This is also known as the input side, and the secondary is the output side. It doesn't matter which one you call it. I'll probably use both. I think these problems have input and output because it's a little bit easier to visualize. All right, what's going into the transformer and then what's coming out of the transformer. All right, so let's take a look. All right, so for this transformer, it gives us the input statistics and the output statistics. So we'll just work it in that last equation. So the input, all right, has 10 coils, all right, and it has an input of 30 volts. Now over here, remember, coils are on top, voltages are on the bottom. So how much voltage will it have for the output if the output side has 50? And there's our equation. Now we have to do algebra, cross multiply. So the V is on the bottom on this side. That means it goes to the top over there. Basic first grade algebra. All right. That gets multiplied over 30 times 50. And we shouldn't even need to go to our calculator at this point. We can see we have output is equal output equals 30 times 50. All right, which is 3 times 5, which is 15. And then there's 2 more zeros left. All right, that 0 and that 0. And this 10 is on top over here, so it gets put on the bottom over there. It gets divided over. So divide that over, and you see one of those zeros canceled out one of those zeros. So we are with an output voltage of 150 volts. And this makes sense because when we were talking about our transformers, we said the more coils you put on the on output side, it's a 1-to-1 ratio. If you increase the coils, you increase the voltage on that side. And you can see we have more voltage on the output side, so more coils on the output side, so we'll get more voltage on the output side. All right? Now let's look at our next transformer problem, because it's a little bit different. Okay, so from reading this question, notice they're not talking about the coils in the transformer. They're talking about input voltage, input and output voltages and currents. All right. So in our discussion on application of electromagnetism, we talked about it. It seemed like a transformer can give us free voltage. Well, that kind of violates the law of conservation of energy. So if our voltage goes up, the trade-off is the current actually goes down. All right. And that is from conservation of energy, which goes to power, which leads to here. All right. So in this problem, we can just plug in these values that they gave us. All right. The input had 2 amps of input current, and the input voltage was 50. All right. That's coming into the one side. Leaving the other side, we want to know how much current, which is the output side, when there was only 5 volts on the other side, all right, on the output side. So we don't need our calculator here either. We have 100 on this side equals 5. Notice that gets divided over there, simple math, simple algebra, first grade algebra. And I equals 20 amps, all right? And does this follow? That's amps. Over to here, went from 50 down to 5. So if we decrease the voltage, that means the current will have to go up 20. All right. And with that, that concludes our equations and our mathematics on electromagnetism. So thanks for watching, and see you when I see you, even though I don't see you right now. But see you when I see you.